Okay, so in this lesson, we're going to be talking about curve sketching. And curve sketching is now where we're going to take a lot of the things that we've been learning thus far about derivatives, about functions just in general, and utilizing that in order to sketch some graphs. Okay, we actually now have a lot of information about the function in terms of graphically, right? We can utilize that in order to sketch our functions, right? So we're going to use some algebra and calculus to determine the following. And we have these A through G, and you're going to need to know all of these. 1, we're going to start out with finding the domain. 2, we'll find the intercepts for the function. 3, we're going to be looking for its symmetry. And we'll talk about symmetry in a little bit, but basically this is even or odd, and if the function is periodic. Asymptotes, vertical, horizontal, and maybe even slant asymptotes. Okay, intervals of increase or decrease, relative extrema, and our concavity and inflection points. All right, so you're going to want to make sure that you've gone through and you've done at least some of the work for all of these pieces because it's going to make curve sketching a lot easier. Okay, this is kind of one of those things that follows naturally from the work that we've been doing in this chapter so far. So let's consider the function y equals 2x squared over x squared minus 1. So the first thing that we're going to do is we're going to determine the domain. Okay, and so the domain, if we look here, we're going to see that x squared minus 1 cannot equal 0. Okay, that's our problem because that's the denominator can't equal 0. So that means x minus 1 times x plus 1 cannot equal 0. And so consequently, what we get here is that our domain, D, is all the values of x, right, such that x does not equal 1 or x does not equal negative 1. Okay? Or literally, you could also say that that's going to equal negative infinity to negative 1, union negative 1 to 1, union 1 to infinity. Okay? That's your domain. All right? So basically, we're going to have a whole, in this case, it's going to end up being an asymptote. We're going to end up with vertical asymptotes at negative 1 and 1. So that's our domain. Next up are our intercepts. And our intercepts, if you remember, this is the x and y intercepts, right? So that we got to have some algebra here, okay? And the x intercepts are going to be particularly important because those are going to be the end up being the roots of our equation. But the y intercepts are also going to be kind of handy too because it might actually help us to draw or sketch our curve. So we're going to let y equal 0, okay? And so that's going to be 2x squared over x squared minus 1 equal to 0. And since the bottom can't equal 0, that's going to mean that 2x squared is going to equal 0. So x has to equal 0, okay? All right, so we have an x-intercept at 0, 0, right? Remember, x-intercepts, we set y equal to 0 and then solve for x, okay? And then if we let x equal 0, okay, we already know that we're going to get 0, 0. Let's just confirm that that's the only one. We're going to get y equals 2 times 0 squared over 0 squared minus 1, and that's 0. So that's our x and our y-intercept, okay? So x and y-intercept. So that's just a little bit of an algebra refresher, right? Okay. For y-intercepts, we're going to set x equal to 0. Next up is symmetry. So symmetry is determining whether or not our function is even or odd, okay, or if we might have periodicity, right? So remember we have f of x equals 2x squared over x squared minus 1. What you'll want to notice is that because the powers here, that's a 2, 2, and a 0, okay? That's one of the 0 function, or actually it's x to the 0, right? Okay, negative 1 times x to the 0. This is actually going to end up being an even function. Specifically, if I plug in f to the negative x, that's going to end up equaling 2 to the negative x squared divided by negative x squared minus 1, and that ends up being 2x squared over x squared minus 1, okay? which is just equal to f of x. So if you remember, that's the definition of even. You may want to go back and review what it means to be even and odd. That actually is in 1.1. Okay, and there's a little video on that inside of the modules. So that's the definition of even. We see that this is an even function. That means the curve is symmetric about the x-axis. So it's going to be symmetric on either side of the x-axis. All right, so if we actually can draw one thing on the right-hand side of the x-axis, the positive side, we know that the negative side is going to look exactly the same. Okay, now let's go on to D. Okay, D is our asymptotes. Now what we have here is we have both negative and we have both end behavior asymptotes, horizontal, right? And we have our vertical. For our vertical asymptotes, we already know that x squared minus 1 equals 0 when x equals 1 and x equals negative 1. So our vertical asymptotes are those ones. Are x equals 1 and x equals negative 1. Now we want to actually find our end behavior. So we're going to take the limit as x approaches infinity, okay, of our function 2x squared over x squared minus 1. And that's going to end up equaling, we've got infinity over infinity. Woo! We got an indeterminate form. Okay? All right? But we can actually, I think probably rather than using L'Hopital's in this case, what we can do is we can multiply by 1 over x squared to the top and bottom. Right? Just utilizing some of those limit properties that we had from chapter 2. Okay? So this ends up giving me 2 over, 1 minus 1 over x squared. And that's the limit as x approaches infinity. Well, this thing is going to then just equal to 2 over 1, which equals 2. So the end behavior for the limit as x approaches infinity is, right, y equals 2. Okay, so that's one of our horizontal asymptotes. Okay? Now what about the limit as x approaches negative infinity? So this is the positive end behavior. And this one here is going to be the negative end behavior. Okay? So we got the limit as x approaches negative infinity of 2x squared over x squared minus 1. And then we're going to do the same thing. We're going to divide by 1 over x squared and 1 over x squared. And this will equal the limit as x approaches infinity of, again, 2 divided by 1 minus 1 over x squared. And that, again, is just going to equal 2. So we have just the one horizontal asymptote, okay, but it's got end behavior going towards this y equals 2. Okay, so we want to notice that. So we've got a vertical asymptote, okay, at x equals 1, and a second one at x equals negative 1. And we've got one horizontal asymptote, y equals 2, but it's going to be going in both directions, right? So as we go out towards a negative infinity and infinity, y is going to approach 2. Next up, we're going to have E, and these are intervals of increase and decrease, okay? And so for determining intervals of increase and decrease, once again, we'll take f of x equals 2x squared over x squared minus 1. We're going to need to find f prime. So f prime of x is going to equal 4x. Excuse me. I was just about to use L'Hopital's. So we'll actually use the quotient rule. So we'll let g of x equal 2x squared. So g prime of x will equal 4x. And then we'll have h of x equal x squared minus 1. And h prime of x will equal 2x. So consequently, f prime of x will equal 4x times x squared minus 1 minus 2x times 2x squared, all divided by x squared minus 1 squared. This will then equal, 4x cubed minus 4x minus 4x cubed, all divided by x squared minus 1 squared. This then is going to equal negative 4x over x squared minus 1 squared. Okay? Now, let's go find our critical numbers. So we're going to have not differentiable at the points that you actually kind of expect, or should be expecting at this point. And that's going to be for x equal to 1 and negative 1 at our asymptotes. So that's where we actually have our function not differentiable. We're going to need to make sure that we include those, though, when we go in and we check for increasing and decreasing. Okay? Then the next piece is to notice, right, when negative 4x over x squared minus 1 squared is equal to 0, that's actually when negative 4x equals 0, and so that's when x equals 0. Okay? So that is our other critical number. Okay? So now I've got something that I can go in and I can check. I'll have 0, I'll have negative 1, and I'll have 1. So we'll go in and test. So we'll start out here, and we want to find f prime of, say, for example, negative 2. And that's going to end up equaling 8 over 9. And so that's positive, right? And so that means that we're increasing, that the function is increasing from negative infinity to negative 1. Then we'll find f of negative 0.5, and that ends up equaling 3.555, basically, repeating. Okay? And so that's also positive. And so we've got, that's increasing. Then we have f of positive 0.5, and that's going to equal negative 3.555 repeating. Okay? And so that's negative, and we have that it's decreasing. This is decreasing. And f prime of positive 2 is now going to equal negative 8 over 9. Okay? So that's negative, and it is decreasing. Now, something to kind of just notice here for you math heads and for everybody actually is to just notice, here's the y-axis, okay? And if you notice, they're mirror images of each other, which is exactly what we expected because the function is even, right? Okay, mirror images because the function is even. So that's just something to notice, okay? And it's something to kind of like help you check that you are on the right track, okay? Right? But now we've actually got quite a lot of information. We've got, you know, the places of increasing and decreasing, okay? And we also have where the, this is also going to tell us where our relative extrema are. So now I can actually write where my relative, where my increasing is. So we're increasing on negative infinity, okay, to negative 1, union, okay, negative 1 to 0, okay? And be very careful here to not include negative 1 in there because negative 1 is undefined. It's not differentiable, okay? Then we're decreasing. Our function's decreasing, right? When we go from 0 to 1 and union that with 1 to infinity, okay? And that's where our function is decreasing, all right? Ton of information there. Now, let's go on to f, and that is our relative extrema. And we want to notice only where we change signs in our derivative. So if you notice, that's only around 0. And so 0 is positive as we approach 0, and then negative as we go towards the positive direction. So consequently, 0, or f of 0, okay, which equals 0, is a local maximum. So that's going to be a local max. And that's our relative extrema. Okay? Okay, so now we want to find the concavity and some points of inflection. And so now here's f prime of x. Once again, it's negative 4x over x squared minus 1 squared. All right, so we want to find f double prime of x. Okay, and so we're going to have to take the derivative of f prime. So I'm going to make, I'll make my g of x equal to negative 4x. And so g prime of x will equal negative 4. And then h of x will equal x squared minus 1 squared. And then I'm going to use the chain rule now to find that h prime of x. So you probably want to make sure to go do it through this, make sure you understand what's going on. Is going to be 2x times x squared times 2 times x squared minus 1. Okay? So f double prime of x is going to be negative 4 times x squared minus 1 squared minus, okay, and that'll be negative 4x times, and this will be 4x times x squared minus 1, all divided by x squared minus 1 squared. Okay, so let's just do some simplification before we actually really simplify. So it's going to be negative 4 times x squared minus 1 squared. And this is actually by this going to be x squared minus 1 to the 4th. Because we've got to square it and square it again. The bottom was squared, so this is now in the 4th. Right? 2 becomes 4. And then this is going to be plus, okay, plus 16x squared times x squared minus 1, all divided by x squared minus 1 to the 4th. Okay? And so consequently, what that's going to give me is I'm going to actually be able to factor out an x squared minus 1. So I'm going to get negative 4 times x squared minus 1 plus, and this will be 16x squared, all over x squared minus 1 to the 4th, to the 3rd. Okay, because we factored out one of our x squareds, or one of our x squareds, excuse me. Comes a 3, comes a 1. Okay, so this is now negative 4x squared plus 4 plus 16x squared, all divided by x squared minus 1 cubed. And so that ends up being 12x squared plus 4 divided by x squared minus 1 cubed. And that's our second derivative. Okay? All right, so now what we need to do is find points of inflection. Now remember, points of inflection are only places where this function is going to end up equaling 0. So what we'll do is we're going to set 12x squared plus 4 equal to 0. Okay? 12x squared plus 4 equal to 0. All right? So what that's going to be is that's going to be 12x squared, right, is equal to negative 4. And then x squared is going to equal negative 4 over 12, which equals negative 1 over 3. So that means that we have no inflection point. But that doesn't necessarily mean that it's the same concavity everywhere on the graph. What we need to do is we need to actually, we're going to continue to check, but where we're going to check is we're going to check around our asymptotes. Okay? So we're going to check with regard to, say, for example, we're going to be around negative 1 and 1. Okay? So we'll take f double prime of 0, okay, that ends up being 4 over negative 1 cubed, which equals negative 4, okay? So we're going to be concave down from negative 1 to 1. What about if the value for x is actually less than negative 1? Okay, so like let's say, for example, we take f double prime of 2, okay? That's going to be 52. Or excuse me, f double prime of negative 2. So that's going to end up being 52 over, and this will be 4 minus 1, so over a positive 27. So it's going to be positive. Okay, it's going to be positive, and so hence it's going to be concave up. And then if we take f double prime of 2, okay, again, that's also going to be 52 and over 27. So it's also going to be concave up. Okay, that's also going to be positive. So what we see here is that we have to actually still, even though we have no inflection points, we're going to have to still check for our concavity because we're going to have to check for concavity around our asymptotes. So our curve is going to end up being concave up on negative infinity to negative 1, union 1 to infinity, and concave down on negative 1 to 1. Okay? So don't forget when you're doing your concavity to also make sure to go in and check for your asymptotes as well, or check around your asymptotes as well. Now gather up all the information that we just took. We're now going to go in and sketch the curve. So now I've got all this information. All right, I'm going to draw my graph now, or I'm at least going to try and draw my graph. Okay, and we'll do some curve sketching. The idea here behind curve sketching is to take all the information that we have and make sure that the curve is consistent with that information. So the first thing that I like to do is I actually like to go in and draw in my vertical asymptotes. So I know I have one here at negative 1, or excuse me, at positive 1. And I also have one here at negative 1, okay? And then also I have my horizontal asymptote at y equals 2. So I'm going to draw that one in as well. I'm then going to put in my local maximum. My local max here is at 0, 0, okay, and my intercept. So my intercept, local maximums, that's going to my points, the points that are important for my graph. I'm going to put here. So now that's going to end up making this look like this, okay? It's the local max, so basically it looks like a parabola in between those two asymptotes. Then I know that if I look here, I'm going to see that I'm increasing from negative infinity to negative 1, okay? So that means, right, that I'm going to be going up towards positive infinity. So we're increasing on that graph, okay? And we'll be decreasing from 1 to negative infinity, so we're going to be decreasing down towards the horizontal asymptote, okay? And that's this little piece right here, okay? There we are. Concave up, I'm just going to go check. With this one, the concavity, there's no inflection points, so I know that my concavity's basically got to look this way, but let's just check. So negative infinity to negative 1, am I concave up? Yep. 1 to infinity, am I concave up? Yep. Am I concave down from negative 1 to 1? Yes, I am. Okay. And so consequently, it looks like my curve is completely consistent. I have my domain. My domain is x can equal 1 and x cannot equal negative 1. I have that with my asymptotes. So there it is. There's an example of going through and sketching a curve. Okay. Sketching a curve is really something that just takes practice. I think actually that the book has a pretty good description of how to do it as well. And that'll kind of like remind you of everything that you need to go through. Just a couple of key tips. Go through the process, the entire process of A through G, okay, in order to sketch the curve. Because it's just, not only is it good practice, but it's also, it'll make sure that your curve is actually correct. And this is just a ton of information too, okay? Then the next piece is I draw in my asymptotes, okay? I put in my intercepts and my local minimums and maximums, okay? Then I utilize whether or not the function is increasing or decreasing in order to kind of draw my my pictures, right? Okay, and then finally I'll plug in my before I go in and check the increasing and decreasing. What I'm going to do is I'm going to also put in my inflection points. Okay, so inflection points, local mins and maxes, and any intercepts, right? Any key points. Yes. Then I'm going to kind of draw out whether or not something's increasing or decreasing. And then before I draw it, I'm going to consider concavity, right? Whether or not where the function's concave up and concave down. Okay? So before you finish, okay, always check that your sketch matches your information. Okay? So this completes the lesson. That's curve sketching.